Hello, I'm Jaideep Sen, and I'm going to present this paper ID 1750 at IEEE INDISCON. The paper title is Confidence-Modulated Speculative Decoding for Large Language Models, and authors of this work are Jaideep Sen, Subhasis Dasgupta, and Hipfi Vagela. Let me get into the presentation mode. So, the table of contents, motivation and background, objective of the work, speculative decoding, which is the core of this work, and overview of that, then the proposed method, the experimental setup, results, conclusion, and references. So the motivation for the work is autoregressive decoding is inherently sequential and slow. And the speculative decoding is an attempt to make it faster, but it involves two steps, drafting and verifying. But existing speculative decoding methods use fixed draft length and the rigid verification process, which makes the process slow. And there is a need for adaptation and confidence about decoding. So the objective of this work is to enhance the efficiency of the speculative decoding in large language models, and by dynamically adapting the number of drafted tokens based on the model confidence to reduce the token rollback and verification failures and to achieve a better trade-off between the decoding speed and the output quality. So before we start, we give a speculative decoding overview. It involves two models. One is a heavyweight autoregressive model, which is accurate but slow, and there is a small drafter model, which is fast but less accurate. The process is drafter graces several tokens ahead in a lookup mode and um, in parallel as well. And the AR model verifies each of the generation. If the AR model finds the drafter's job is correct, then it skips ahead. If it is wrong, then it rolls back. So rolling back actually is a costly process, whereas skipping ahead, of course, is a very efficient process, right? This makes the generation faster. So goal is to speed up generation by avoiding one token at a time decoding for the AR model and providing parallelism but limited static design, because as I've already said, the draft length is fixed and the verification is static. It is based on top 1 and top B. Whereas drafter is confidence, it could have actually, drafter is confident, then it could have actually guessed more, but it did not. So there was a wastage of resource. And when the drafter is uncertain, it could, it guesses too many, and then there is a rollback, which is also inefficient. So the proposed method actually involves computation of a confidence score based on the entropy, logic, and softmax at the context. That means entropy is lower the entropy, higher is the confidence of the drafter. The gap between top 1 and top 2 words, in terms of logic, indicates the confidence of the drafter, as well as softmax difference, the probability difference with the top 1 and top 2 tokens, is also an indication of the drafter confidence. What we have done, we have combined these three together to compute a confidence score, and based on the confidence score, we have adapted the drafting window size as well as the verification window size. So when the drafting is confident, that means when the confidence score is high, we have increased the drafter window size and allowed the drafter to, guess more, generate more words, more tokens. And when it has got less confidence based on the confidence score, it automatically the drafting window size is adapted to a fewer tokens, and thereby the drafter's failure chance obviously becomes less, reduced. And verification also, when the drafter is more confident, then there is a relaxed verification process. When the drafter is less confident, there is a stricter verification process, because the chances of generating wrong words or inefficient words are possibly more. So that's why this is an adaptive drafting confidence modulation. The drafting length is adjusted. The confidence weighted function decides how many tokens to generate. It avoids over speculation in low confidence region, improves token acceptance with reduced latency. The verification thresholds vary with confidence, stricter checks when uncertainty is high, more relaxed acceptance when the confidence is high. This is the flow diagram, which we have already discussed. So experimental setup, there are two tasks, machine translation and machine summarization, I mean the abstractive summarization. The dataset used for translations are WMT14 and WMT16, English to German and English to Romanian. And for abstractive summarization, we have CNN Daily Mail dataset. The model is GPT-2 model on which we have worked, and the metrics are BLEU, translation, ROUGE summarization, decoding speed, and token rollback. So BLEU score for translations, ROUGE score for the summarization. The baselines are ER decoding, greedy decoding, and SpecDec. And these are implemented on a single NVIDIA A100 GPU, decoding performed as a batch of 16. Now, these are the machine translation results in terms of speed. So we took transformer base B, that is beam size 5 as a base model, and these are our base speed, which has been taken as 1. And we have seen that how much gain in speed we have got, right? Obviously, compared to speculative decoding, our process is a little slower because there is an adaptation computation going on, right? But we wanted to check that how much is the difference. So we found the difference is not at all high, 4.6 to 4.2, 4.8 to 4.4, and so on. So we have seen the cost of adaptation, computation here in CM-ASD is not high. Now we have seen that how is the BLEU score, right? The BLEU score comparison between CM-ASD and the other methods, and we have found that the BLEU score for this 4 data set are quite high compared to the base, 28.89 to 28.91 to a 32.53 to 32.58. So there is a quite high, so it is comparing BLEU score performance with respect to all the others. So that means even though there is an adaptation, the BLEU score comparison, there is not much of, there is no loss actually in terms of BLEU score. And when it comes to ablation studies, that means how we are gaining by incorporating one by one extra steps, we find that consistently for both token, average token acceptance, BLEU score, drafting speed, as well as, the average time spent in drafting, right? These all the cases, there has been a consistent rise as we go on, incorporating one by one these extra layers. So first we had adaptive drafting, adaptive verification, and confidence, none of them present. So we saw that what is the token acceptance range. Then we have entropy only confidence, margin only confidence, and software max only confidence, and they have added up finally to have a much higher rate compared to the original one. So the ablation studies, and what actually is the best performance for us is the machine translation case, right? Here we saw that with latency and throughput performance, with the increase in throughput size, the latency actually is not at all increasing as much, even with the speculative decoding gave us. Speculative decoding is the yellow line. The current method is the green line. We saw that there is a for less latency even at a higher throughput. AR anyway is losing out with a very high latency as the throughput increases. Okay, then this is the abstractive summarization where the ROUGE 1, ROUGE 2, ROUGE and speed computations are done. There also we find the performance of CM-ASD superior compared to the other baselines that we have checked. The conclusion is that we have found the adaptation really saving the resource, optimizing the resource for reducing the wasted generation as well as wasted verification. It achieves significant speed up 5 times while maintaining improved BLEU and ROUGE scores. It reduces rollback Also, by having a highly robust verification process, the future work includes extending the approach to multimodal generation tasks and exploring Bayesian or embedded-based confidence estimators. These are the references. So I would be happy to take any questions. So let us close this presentation now.